Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is power factor correction. Our objective is to examine the means of power factor correcting an electrical system. We'll examine electrical properties like source current, apparent, real, and reactive power for power factor corrected systems. Power factor correction is often a great nemesis for many first-year electronics students. This needn't be the case. Power factor correction is elegant, cool, and a satisfying real-world application of practical circuit analysis principles. If I was to list my personal favorite electromechanical subjects, power factor correction would be very near the top, if not the top. My hope is that following this lecture, you too will have a greater appreciation of power factor correction, and even if you aren't willing to call it one of your favorite subjects, at least survive a meeting engagement with power factor correction with some level of dignity still intact. This being said, you need to meet me halfway. This lecture operates under the presumption that the viewer has more than a passing familiarity with both AC circuit analysis and AC power calculation. In my personal experience, students having issues with power factor correction don't necessarily struggle with the concepts of power factor correction per se, but rather simply do not possess competent circuit analysis or power calculation skills. In short, if you showed up to this gunfight with a dull knife, be prepared for a quick and bloody end. It is additionally presumed that the viewer has watched both the power and parallel AC circuits and power factor and efficiency in AC circuits lectures. If you recall, the last illustrated examples in these two aforementioned lectures discuss power factor correction on a preparatory level, and this particular lecture operates under the presumption the viewer already has some level of familiarity with power factor correction, introductory as it might be. If you lack the requisite level of familiarity with power factor correction, please review the aforementioned supporting material and return to this lecture when you are so qualified. As a preliminary exercise for our discussion about power factor correction, consider a 120 volt 60 Hz AC source, an electrical load modeled as an impedance of 75 ohms at an angle of 35 degrees at this particular excitation frequency. See if you can solve for the voltage, current, apparent, real, and reactive power, as well as the power factor for the electric load in the present configuration. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Ohm's law demonstrates current through the electrical load will be 1.6 amps at an angle of negative 35 degrees. The phasor diagram illustrates current through the electrical load will lag the voltage across it by 35 degrees. Apparent power delivered to the electrical load is the complex conjugate of voltage times current. Substituting in our given values yields an apparent power figure of 192 volt amperes at an angle of 35 degrees. Resolving this into its real and reactive components demonstrates the electrical load is directing 157.3 watts towards real power and 110.1 VARs towards a reactive interchange. Finally, it can be said that the electrical load has a lagging power factor of roughly 0.82. Let's put these initial figures aside as a basis of comparison for the upcoming exercise. By the way, if your answers don't match those illustrated, you are simply not qualified to discuss power factor correction. If I was one of those teachers you see in bad after-school specials, I'd say, just believe in yourself and you can do anything. But I'm not, and I'm more liable to say, go away and don't come back until you've brought yourself up to speed. Assuming you're still with me, let's examine power factor correction in general terms. Without stretching the truth too much, capacitors and inductors are essentially mirror images of one another in terms of electrical properties. Capacitive elements have negative complex impedance angles, whereas inductive elements have positive complex impedance angles. Capacitive complex impedance magnitude decreases at higher frequencies, whereas inductive complex impedance magnitude increases at higher frequencies. Current through capacitors lead voltage by 90 degrees. In contrast, current through inductors lag voltage by 90 degrees. Reactive power polarity for capacitors is negative, whereas inductive reactive power polarity is positive. I've even heard capacitors taste like chocolate and inductors taste like vanilla. They are total opposite of each other in almost every sense. Bonus points if you manage to trick your lazy lab partner into eating a capacitor or inductor. Keeping with this theme, a power factor corrected circuit is one in which the reactive power of a fixed load is counteracted by an equal yet opposite variable reactive element such that total apparent power is directed solely towards real power and none of it towards a reactive interchange. To say no apparent power is directed towards a reactive interchange is a little bit of a lie. In reality, there will be a continuous, equal, yet opposite exchange of reactive power between the two reactive elements internal to the circuit. However, quite like positive and negative, yin and yang, fire and water, or chocolate and vanilla, they balance each other out such that in summation, there appears to be no total reactive power. It should be noted that most small-scale power factor correction scenarios involve the placement of a variable power factor correcting capacitor in parallel with an electrical load that exhibits inductive characteristics and not the other way around. The reason behind the regularity of this arrangement is that ordinarily the electrical load in question being power factor corrected is in fact a motor which ordinarily exhibits inductive behavior. Conceptually, you might think of a power factor corrected circuit in the following fashion. For a perfectly power factor corrected circuit, the moment the inductive portion of the load is building and sucking in current of a given magnitude, the power factor correcting capacitor is discharging that exact same amount of current. In this sense, the power factor correcting capacitor is dumping all its stored power into the inductive portion of the load just when it demands it. At the opposite end of the cycle, the moment when the inductive magnetic field is collapsing and squeezing out current of a given magnitude, the power factor correcting capacitor is charging and sucking in this exact same amount of current. In this sense, the inductive portion of the load is dumping all of its stored power into the power factor correcting capacitor just when it needs to get rid of it. This is perhaps the origin of the terminology absorb and supply with respect to reactive power. Inductors are known to absorb or consume reactive power and are so indicated with a positive sign. Capacitors, in contrast, are known to supply reactive power and are so indicated with a negative sign. Again, I find these terms somewhat regrettable since reactive power is not truly consumed nor supplied, but rather continually exchanged. However, in this application, I do find they're somewhat fitting. It doesn't mean I like it, but I can understand it. In a perfectly power factor corrected circuit, an equal and opposite amount of reactive power simply bounces back and forth between the two reactive elements. Importantly, given this cyclical exchange occurs within the circuit itself, the source doesn't need to provide reactive power over a distance. As such, we might expect source current to not only be smaller in magnitude, but also perfectly in phase with the supply voltage. In summary, a power factor corrected system will draw less source current, yet experience the same amount of real power. This is the single most fascinating aspect of power factor correction, and the reason why it's one of my favorite subjects. By balancing the reactive power requirements internal to the circuit, you get the same results for less input. Let's return to our previous illustrated example and see if we can power factor correct it, and then compare and contrast the electrical properties with our previous implementation. As our previous calculations demonstrated, our electrical load exhibits inductive characteristics, and we need to install a variable power factor correcting capacitor in parallel. Then, we need to adjust this capacitance value such that power factor corrects this system. Don't make power factor correction hard. Capacitors and inductors are essentially mirror images of one another. Given we previously demonstrated that the load is consuming positive 110.1 VARs of reactive power, the power factor correcting capacitor needs to be adjusted such that it will supply negative 110.1 VARs of reactive power. Can you dig it? Capacitors and inductors have equal and opposite natures. The harder portion of power factor correction deals with determining the impedance and actual capacitance value that will achieve this ideal scenario. This being said, it's not that hard if you're skilled at manipulating Ohm's law and/or the AC power equation. There's a couple means of arriving at these figures. However, I find the easiest, most direct means of doing so is to use this formula. Apparent power equals the complex conjugate of voltage squared divided by impedance. In this case, we know that the variable power factor correcting capacitor needs to supply 110 volt amperes at an angle of negative 90 degrees of apparent power. Given we know our desired apparent power figure and we know the voltage in this perfectly parallel circuit, we can rearrange this equation to solve for impedance, where impedance equals voltage squared divided by the complex conjugate of apparent power. Don't get mixed up by angles and signs here. You know the apparent power for the power factor correcting capacitor has an angle of negative 90 degrees. You know capacitive reactive power has a negative value. You know capacitive complex impedance has an angle of negative 90 degrees. Just solve for the magnitude of the impedance, add an angle of negative 90 degrees behind it, and call it good. Substituting in our given values, we arrive at an impedance figure of roughly 130.8 ohms at an angle of negative 90 degrees. All we need to do now is to calculate the capacitance value necessary to achieve this desired impedance at the given excitation frequency, in this case 60 Hz. Given we know our desired impedance magnitude and the excitation frequency, we can rearrange the capacitive complex impedance formula to solve for capacitance, where capacitance equals 1 over 2 pi f times the impedance magnitude. Again, don't worry about angles. You know capacitive complex impedance has an angle of negative 90 degrees. Just solve for the capacitance value that yields the desired magnitude. Substituting in our given values, we arrive at a capacitance of roughly 20.3 microfarads.